All right, so thanks very much for both of the chance to speak in the members seminar and for coming. So this is going to be an extremely superficial account of an ongoing project with Shiel Ganatra and Nick Sheridan. There's an archive reference which sort of explains basically what we're doing. So this is going to be about the relation between certain different formulations of mirror symmetry for Calabi-Yaos. So what I'll say today will be frustratingly superficial for the experts, but I'll be at tea. So here's the gist. So suppose that X is a Calabi-Yau, so a smooth, and for these purposes, projective Calabi-Yau manifold of dimension n over C. So that's to say it's a complex submanifold of complex projective space Cp capital N for some capital N, compact submanifold, and it admits a holomorphic volume form. That's the Calabi-Yau condition. And as such, it's a symplectic manifold, so X inherits a real symplectic form, in fact a Kähler form, omega from Cpn. And as such, we can think of it as a symplectic manifold and compute symplectic invariance. And the result that I want to say something about today says the following: if homological mirror symmetry holds for the symplectic manifold X omega, relating categorical invariance associated with that to algebrogeometric invariance, categorical algebrogeometric invariance for some mirror Y, which is, for these purposes, a smooth projective Calabi-Yau n-dimensional variety defined over the field of finite tail Laurent series with complex coefficients. Okay, so if this categorical relation holds, and there'll be more about that presently, then something that is much less abstract is also true. So certain Gromov-Witten invariants of the symplectic manifold X, which enumerate, in a precise sense, holomorphic maps from the two-sphere to X up to reparameterization of various degrees, then those can be interpreted in the algebraic geometry, specifically the world of variations of Hodge structures of Y. Okay. So an abstract statement about equivalence of categories ends up implying statements about how many rational curves there are. To To what extent is y unique? It's not quite. So here y is just sort of characterized as having this categorical equivalence, and with that characterization, it's not quite unique. There can be flops relating different mirrors, for example. I'm sorry?
The parameter Q.
Yeah. Yes. More to come. So specifically, I'm going to at least pin things down precisely on the Gromov-Witten side of this. So if I take the following vector space, so the singular cohomology of X with complex coefficients, it's just a complex vector space. And the linear map from V to power series in V, and it's the map which is the so-called quantum product with the symplectic class. Okay, so that thing has such an interpretation on Y under the homological mirror symmetry assumption. So let me just say what this R is. So the map R can be characterized as follows. Suppose you take a cohomology class X and apply R to it, and then you cup it with some other cohomology class Y, and then integrate over X. Okay, so if you know all such values which are power series, then you know R, and the answer is that is a generating function for this Gromov-Witten invariant. Okay, so this is a count of maps U from the two-sphere to X, holomorphic, of degree D, with the property that there are if you fix 3 points in the domain, then those have to map to certain prescribed cycles. So those are going to map to chosen cycles that are dual to the symplectic class to X and to Y. Precisely which cycles you choose doesn't matter. Okay, so that's what we can interpret at this point. Yeah. Sorry, was there a question?
I'm trying to formulate.
Sure.
Well, R is homogeneous in some sense.
Homogeneous. Yes, it's degree preserving.
X a little y or some complementary degree.
Sorry, I beg your pardon. It's yeah, they will have to be complementary degrees. This says the integral of the pullback via U of the symplectic form over the two-sphere. Okay. So such a relation, a logical relation in which open string invariance, homological mirror symmetry, implies mirror symmetry for closed string invariance, Gromov-Witten invariance, and so on, is very much in line with what the string theorists predicted. It's also in line with what's understood from topological field theory, the work of Kontsevich, Costello, and so forth. But nonetheless, this is a new theorem. So, for example, a key example is that we can take X to be the quintic threefold. In CP4. There's a standard mirror, which you can think of as a family over the affine line A1. The generic fibers are Calabi-Yau threefolds. Some of them are singular. In particular, over 0, it's singular. And now we come to the question of well-definedness of Q. So, so we're going to think about formal disks around 0 in A1. So that's to say, we're going to think about scheme-theoretic maps from spec of a power series ring to A1. Well, such a thing amounts to a power series and that it's around 0 says that the leading term vanishes. And so Nick Sheridan, generalizing Seidel, showed the following. There exists such an M, such a power series essentially, and a quasi-equivalence from, well, a version of the Fukaya category and it's a version that's defined over the field K of Laurent series with the derived category dB co of Z, where Z is the family over the formal punctured disk that I get by using the coordinate m and inverting q. Okay. So.
This is a statement of some this is a mirror symmetry statement. It's for some specific or is it
Sorry, was the question, is M explicit? Yeah?
No.
No.
What are X and Y in this set?
Oh, so X is this quintic threefold, and Y is this standard mirror. M, this mirror map in this theorem, is so far not explicit. It's some power series. So M comes from some unknown F, which just all you can say is that it starts at this point is that it starts with Q. Okay, but we can now do better.
Why does it not matter which x you took?
Which X?
You took one, you said one, threefold.
This is a so we're doing symplectic geometry here. So the Gromov-Witten theory is a symplectic deformation equivalent. Is a symplectic deformation invariant, and since all quintic threefolds fit into a connected family, they are all deformation equivalent.
That if you have automorphism of x coming from monodromy, this will have a counterpart for y.
Yes, absolutely. And one expects to be able to set things up in such a way that that monodromy corresponds to tensoring by an ample line bundle as an equivalence, an autoequivalence of the derived category. There's then also an interesting natural transformation from the identity to that autoequivalence. Well, okay, maybe I shouldn't get sidetracked with that. Okay, so what we show in this context is that the Gromov-Witten invariance of the quintic threefold, so I'll just take 3 copies of the hyperplane here, hyperplane class, and form this generating series. Okay, so this, by the way, is very well known to be an interesting series. This begins 5 plus 2, 8, 75Q plus something. Okay. And this one ends up being expressible as a Yukawa coupling for the mirror. So something like this. For a volume form omega on Z. So nabla here is, well, okay, so I'd like to say it's the Gauss-Manin connection in algebraic de Rham cohomology. For technical reasons, we have to replace that by something a priori different, and that's the version of the Gauss-Manin connection constructed using non-commutative geometry, the derived category, by Ezra Getzler, which one then transfers to algebraic de Rham cohomology. It's surely the same as the Gauss-Manin connection, but this is an issue that doesn't seem to have been sorted out yet. Up to a power series, yeah.
Yes. So
Yeah, up to a scalar. So, and I'm sorry, I didn't quite follow. Well, you should think of, in complex analytic terms, think of omega as a 3-0 form. When you hit it with the Gauss-Manin connection, you know, it hurts the Hodge filtration by at most one step at a time, and so it's only after hitting it 3 times that you get something which has a 0-3 component, and that's what you're going to wedge together and integrate to get a number. If you only did this twice, you would certainly get 0. Okay. And so moreover, both the volume form and the mirror coordinate m, which are a priori determined up to multiplication by scalars in this field, so that's a lot of ambiguity, are in fact pinned down by, well, the leading terms plus how they behave under the Gauss-Manin connection in a way that one can write down. Okay, so so this actually becomes a concrete thing, and so this this formula here. Sure. Yeah. So what you want to do is to make sure that when you apply the Gauss-Manin connection to omega, you take it sort of strictly downwards in the monodromy weight filtration. And moreover, you then characterize m by saying that if you differentiate in the direction q d by dq, and you hit omega twice, then you go down and down again in the monodromy weight filtration. So star was, first predicted in 91 by Candelas, De La Ossa, Green, and Parks, and proved, of course, with the real Gauss-Manin connection, not this Getzler version, by Giventhal and Yu, Yan, Yao. So that result is not new, but nonetheless, doing it it's a more conceptual proof than we've had before. Previous proofs. So we use Sheridan's theorem, which is homological mirror symmetry, and then we use Ganatra, Sheridan, and myself, which is this implication of Hodge-theoretic mirror symmetry. Are there new cases you're going to say? Yeah. No, we're at a primitive stage, but we have kind of grand schemes which should do vast swathes of examples at a stroke at some future date. So what? In general, I expect that's true. I mean, Orloff has a very interesting derived Torelli theorem for K3 surfaces, so which one could interpret it as saying that in that case you could go backwards. Where do I want to write? Over here. So yeah, actually, I'm sorry. I want to write on a longer board. The by an integer. Yeah, I mean, it's certainly easy to say what happens to the Gromov-Witten invariant scale in an appropriate fashion, and I think there's a simple pullback relation on the right, but I might have it wrong. There's a sort of a hoped for big picture of mirror symmetry at this point, into which this will eventually slot, we think, which is that you start out with X some degenerating Calabi-Yau. So a fiber of some family where the special fiber is as degenerate as a Calabi-Yau can be. Toric degeneration, for example. Maximally unipotent monodromy would be a sensible thing to say. And then one hopes that will imply that there exists a Lagrangian fibration, necessarily by tori. So this is your 2n-dimensional symplectic manifold. This is some middle-dimensional manifold. And this is supposed to be such that this is a surjective map, and omega on its kernel vanishes. So to the extent that it's non-singular, it's a Lagrangian fibration. One then hopes, and this is the subject of remarkable progress by Fukaya and Abu-Zaid, that one can use F, perhaps a little more, to construct an intrinsic mirror X check, which will be somehow a rigid analytic space. And one will have homological mirror symmetry relating the Fukaya category of X to... Yes, over the field of Novikov series with its valuation. And that's that's something for which one hopes that homological mirror symmetry, a relation between the Fukaya category of X and the derived category of the mirror, will hold in a rather tautological fashion. Then homological mirror symmetry ought to imply that the Gromov-Witten theory of X is interpretable in terms of the Hodge theory and more of the mirror. So Hodge theory, at least if one is doing genus zero Gromov-Witten theory. And so what we're doing is some version of this implication, which we hope will be part of a much bigger picture. Yes, that's right. This one starts. One way to interpret this is that X comes with a symplectic form, but you can also scale that symplectic form by real scalars. So in some sense, it forms a one parameter family, and that's supposed to correspond to the one parameter. So you sort of have this Novikov field, which is in some sense a one-dimensional base, and those are in some sense mirror. And then there's a more elaborate story with families. Okay. So let me talk a bit about Fukaya categories. So those of you who've been irritated by my banding about of this term can get some sense. Fukaya, Ota, and Ono, I guess, are the most relevant authors to what I'm about to say in the next few minutes, though Seidel's foundational work is also relevant. So you take your compact symplectic manifold X, and you take a pair of compact Lagrangian submanifolds thereof, middle dimensional submanifolds on which the symplectic form vanishes, and we're going to try and build a chain complex. So we're going to try and build the Floer chain complex CF L0 L1, which is a vector space over a base field with a differential on it. Ungraded in this generality, or at this stage. And then we'll define the Floer cohomology to be the cohomology of delta. And so let's assume for simplicity that these two are transverse. So, schematic of two transverse Lagrangians in R2. And then in that setting, it's legitimate to define this complex to be, well, generated over the base field by the finite set of intersection points. Okay, so lambda is the base field, and it's going, in a moment, it's going to be specified. I meant to say the following. So the goal is to set this thing up in such a way that that once you pass a cohomology, you get something with good invariance properties. Namely, it's invariant under Hamiltonian isotopies of L0 or of L1, which will not be true of the chain complex. Okay, so so now we need an endomorphism of this thing. So I have to tell you what that does on an intersection point. And necessarily that's going to be a sum over intersection points y of matrix coefficients nxy times y. And so the point is, what are the matrix coefficients? And this one is supposed to be a count, in some sense, of maps U from a doubly infinite strip into X that are J holomorphic, where J is a fixed almost complex structure on X compatible with your form, your symplectic form. And the constraints are that the boundaries of the strip map to L0 and L1. And as you go off to infinity, you're asymptotic to the chosen intersection points, X and Y. So it's often helpful to think of this strip as in a different model that's conformally equivalent, which is as a disk with two boundary points deleted. Okay, so well, certainly there's a translation action on this moduli space, and so I want to count modulo translation. Then there are a whole lot of steps in understanding what you mean by counting such things. So first of all, so you only count U of Fredholm index 1, so such maps are cut out by an elliptic equation with reasonable boundary conditions. The linearized equation defines a Fredholm operator. You want Fredholm index 1, which means that these objects modulo translation are sort of isolated, and you want them to be cut out transversely by their defining equations. Let me say things in the order I planned. And now the thing is, so you're now sort of trying to count a discrete set, but not yet a finite one. Okay, so that's no good. So the fix is that you keep track of the area with respect to the symplectic form of these strips, whereupon Gromov compactness gives you some kind of a compactness theorem for strips with bounded area. So this sort of basic geometric point, Gromov compactness, has a sort of a critical role in how we algebraize this theory. So we can take for our coefficients the Novikov field, lambda, which is a gadget that will allow us to record these areas in the coefficients. So lambda, it's a field of power series of a kind. You could write them as sums of ai q to the ri, where here the ai let's take to be complex numbers, so that's not essential. What is essential is that the Ri are real numbers. I'll arrange them in increasing order, and I want them to increase towards infinity. So, of course, really, this is just this. You could think of this as a function from the reals to the complex numbers with some support property. Okay, and in that sense, it becomes a ring, and it's actually an algebraically closed field. Excuse me. And it comes with evaluation. Which takes this power series, and we can assume that A0 is non-zero, and maps it to the leading exponent R0. So this is an algebraically closed field of characteristic 0 with this sort of non-Archimedean valuation. Okay, so this one, this area gets fed in as q to the area. The coefficient is essentially is up to sign issues is the number of such maps. Okay, so there are signs. Oh, look. Okay, I'm not going to write anything. They come from spin structures on the Lagrangians. In particular, the Lagrangians we'll think of as oriented, and that means that they have their intersection points have Lefschetz signs, and so you get a z mod 2 graded complex because you can assign to the generators of the complex a parity. So at this point, so the idea is that delta squared equals 0 comes from degenerations of index 2 holomorphic maps to pairs of index 1 holomorphic maps, which is part of Gromov or Gromov-Floer compactness. But there's still a problem. With disk bubbling, the point being that you can run into trouble with configurations like this, where you have the kind of disk that you want, but in addition a bubble attached to one or other of your Lagrangians, a holomorphic disk there. This is a big issue, and that there are fixes involving bounding cochains, Marov-Bartan equations, and from now on I'm going to pretend it's not there. Finally, I'll remark that when the first Chern class of the tangent bundle is trivialized, along with the so-called Maslov class of your Lagrangians, you get a lift to a z grading on your complex. So the mod 2 Lefschetz numbers can have integer lifts. Mm. I'm sorry?
When you had C1x, this is
integral. Oh, I see what you mean. Trivialized. Yes. Trivialized as an integer. Yeah, I mean, fix a C infinity holomorphic volume form. It'll only matter up to homotopy. Okay. So in the Fukaya category, Fukaya categories have a wonderful way of eating up a great chunk in the middle of one's lecture. Okay, so so you have objects which are Lagrangians plus data as above, spin structures, trivializations of these things, etc. The Hom spaces, at least when your objects are transverse, are these Floer complexes formed by the intersection points, and then you have operations mu d which are multilinear operations on Hom spaces that you think of as compositions. So I'm using kind of composition notation. So you have L0, L1, L1, L2, etc., and eventually LD minus 1 LD, and the output is in L0, LD with a shift in degree, satisfying this higher associativity or A infinity relation. And I'm not going to write it down, but I'll say that mu1 is the differential delta, so mu1 squares to 0, and the A infinity relation generalizes that. And furthermore, I'll say that these come from counts of holomorphic polygons in your manifold subject to Lagrangian boundary conditions. And I think I'll leave it at that. There's then a formal process, meaning something that you can apply to A infinity categories generally, which converts this gadget into some kind of module category. So I'll just write fx primed. So this is now a differential graded category closed under mapping cones and passing to direct summands. And it's that we will use as a more accessible manifestation of the Fukaya category itself. And so the HMS question is, when can one interpret this gadget as sheaves on some kind of a space, so really coherent sheaves on some kind of an analytic space, a locally ringed space over the field lambda. So this question can be made precise using Tate's language of rigid analytic spaces. And so that's what we're trying to produce and to study, such a mirror space. Yes. Yeah, and that's the natural thing. So really here I mean, a derived category of coherent sheaves that naturally takes as its coefficients the base field of this mirror object. Okay. Well, so brave people like Mohammed Abu Zaida working hard at this. My knowledge of algebraic geometry is not great, but my knowledge of rigid analytic geometry is non-existent. And so I prefer a more algebro-geometric version of this question. Where the mirror space is a variety over the Novikov field lambda, or even over the Laurent series field, which sits inside lambda. Projective, smooth projective variety. Okay, so for this, so what we do is that we take our symplectic object x actually to be, a smooth projective complex manifold equipped with an ample divisor D, And for today's purpose, I'll take that divisor to be smooth. Simple normal crossings would be OK. And omega is going to be a Kähler form that's supported on D, and more precisely, so omega on the complement of D will be expressible as ddc of a Kähler potential H. So some exhaustion function on x minus d, which takes some logarithmic form as you approach d. Not well. I mean that's a way of producing such a function, but I mean, yeah. So okay. So you have the Cayley metric on the variety itself, but you don't need to fix a metric on the line bundle. Okay, so we're going to restrict the Lagrangians L in two ways. First of all, we're going to insist that they lie in the complement of your ample divisor. And second, we'll insist that they're exact. So what that means is, so here's a primitive for omega minus dc of h, excuse me. When I restrict that to a Lagrangian submanifold, I necessarily get a closed one form because it's Lagrangian. And I actually want that to be exact. So d of some function on L. So that actually affects, it's not immediately visible, but it affects a pretty huge technical simplification in the Flirt theory. But what you can do is that you can algebraically, is that when you look at the holomorphic polygons defining the A infinity operations mu d, you weight them not by q to the area as before, but instead by something which is almost the same, which is q to the intersection number of your polygon with the divisor d. Up to something bounded, it agrees with the area, but the point is this lives in this Laurent series field now. Okay, so okay, so this gives rise to the relative Fukaya category, f of x comma d over k. And what's the relation? Well, over the Novikov field, this one sits inside the absolute one. After all, an exact Lagrangian in x minus d is an example of a Lagrangian in x. In general, there's a big difference between these two. This one, for example, could be empty and this one not. But in mirror symmetry situations, that part of the conclusion is going to be that this will be an equivalence. So homological mirror symmetry relative to D would say that this relative category, or rather this formal enlargement thereof, would be quasi-equivalent over K with, well, perfect complexes, let me say, on Y for some smooth projective Calabi-Yau y over k. K is Lorentz series, yes. So, so if you're in a situation where homological mirror symmetry in this sense applies, then that tells you certain things of a purely DG categorical nature about the Fukaya category. So in particular, it tells you that this thing is a smooth DG category. Okay, so I'm not going to write down the definition right now. It has to do with sort of resolving the diagonal. But it's a property that's purely categorical in nature and is enjoyed by derived categories of smooth varieties. And this is a property that's been emphasized by Kontsevich as well as Kaledin and others. So its relevance to algebraic geometry is well known. Yeah.
f(x, d) and not f(x, d, h.
Oh, there's an uncountable amount of data which I have failed to notate. Yeah, it depends on, yeah. It depends, I mean.
Also, the right-hand side, the first y, it doesn't depend on d.
I'm sorry?
The right-hand side, first y, does it depend on d?
On d. Well, you know, this is a now, I mean, that has to do with the reduction from lambda to k, which is a particular model for this algebrogeometric gadget. So yeah, that could depend on d.
You have to take just the usual inclusion, right?
Sorry?
K is just included in lambda.
Well, that's right, but to define a variety, you know, to lift the definition of the field of definition of a variety from lambda to a subfield thereof is data.
So you mean the m in the beginning of the lecture?
Well, it's related to that. Let me finish off because I'm almost at the bell. I'd like you to think of this relative situation as not being particularly good for defining things that are invariant, but being good for giving you convenient models to work with. So it turns out that smoothness interacts very nicely with the symplectic geometry of the Fukaya category or the relative Fukaya category, and also with that of quantum cohomology. I think that's a point that's where some relevant names are Abu Zaid, Ganatra, and others. So we have the theorem that when the relative Fukaya category of a Calabi-Yau X is smooth and non-empty, then this category determines closed string invariance or quantum cohomology and its algebraic structures via Hochschild invariance of the relative Fukaya category. So Hochschild homology, Hochschild cohomology, periodic cyclic homology are all relevant here. And so this is a rather imprecise statement. So, in particular, so one has that the natural map from Hochschild homology to quantum cohomology is an isomorphism. And that, so just to finish off, so that leads to the following result, which is that when homological mirror symmetry holds for x relative to d versus this mirror variety y, there's an isomorphism of mod 2 graded k vector spaces. On one side, the quantum cohomology of x, the small quantum cohomology, and on the other side, the algebraic de Rham cohomology of the mirror, intertwining various algebraic structures. So in particular, the quantum differential operator, which is the endomorphism of this one, takes this form. So the second term is this operator R from the beginning, corresponds to Getzler's version of the Gauss-Manin connection acting in the direction qd by dq. And it's sort of by taking residues of that operator, essentially, that one gets the result stated at the beginning, which is that you can really express this operator R in terms of variations of Hodge structures on the B side. Sorry for overrunning. Thanks.